In this video, we're going to talk about supplemental examples from 9.3. Let's look at the first one, which is like problem number 7 from 9.3. Confirm that the integral test can be applied to the series, then use the integral test to determine convergence or divergence of the series. So we need to make sure that it meets the criteria, that it's positive, continuous, and decreasing. If we're going to use the integral test, now we actually can use the geometric series test here because we have this as n equals 0 to infinity of e to the negative n plus 1 is going to be n equals 0 to infinity of e times 1 over e to the n, like that. And this will be my a naught, and this will be my r. And my r is between 0 and 1, so this converges. S is going to be equal to e over 1 minus 1 over e. It's going to be e squared over e minus 1. So I can not only tell you that it converges, but what it converges to. Let's go ahead and use the integral test here. So this f of x here that we're going to test is going to be 1 over e to the x. And so this is 1 over e raised to the x. Part 1, since 1 over e is positive, 1 over e to any positive power, any power really. But I'll say to any positive integer power, natural number power, is also positive 2. And if we wanted to look at the graph, we could see that it's always greater than 0, like this. So we know the domain of this function is negative infinity to infinity, and the range of this function is 0 to infinity. So you could also go for that with a range and say that the function is always greater than 0. 2, it's continuous. The function here has a domain of negative infinity to infinity. It's continuous on its entire domain of negative infinity to infinity. So it's going to be continuous on the interval of interest from 1 to infinity. And then f prime of x is a negative e to the negative x, so negative 1 over e to the x. So no critical numbers. Here, but if I look and pick a test point like 0, then this is going to be a negative 1 there. So it's less than 0 and decreasing everywhere. So it's decreasing from negative infinity to infinity, which I see on the graph here, but I just proved it with calculus here. So we're going to be positive, continuous, and decreasing. on my interval from 1 to infinity that I'm interested on. So we can use the integral test. That was all preliminary. Let's go ahead and use the integral test now from 1 to infinity of e to the negative x dx is going to be limit as b goes to infinity, 1 to b, e to the negative x dx. And that's going to become a negative e to the negative x from 1 to b, limit as b goes to infinity, limit as b goes to infinity of negative e to the negative b plus e to the negative 1 equal to limit as b goes to infinity of 1 over e minus 1 over e to the b, 1 over e minus 0 is equal to 1 over e, and it converges. So you can see that the integral converges, the series converges, but they don't necessarily converge to the same thing. So summation n equals 1 to infinity of e to the negative n converges by the integral test. Let's go ahead and look at this example, which is like number 17 from 9.3. Confirm the integral test can be applied to the series, then use the integral test to determine the convergence or divergence of the series. So my f of x of interest here is equal to 1 over 2x plus 3 to the third, which is equal to 2x plus 3 to the negative third. So for all x greater than or equal to 1, 2x plus 3 is great. Actually, let me just look here and show you on a number line here that my number of interest, I have no zeros in the numerator. My 0 of the denominator is negative 3/2. And when I put in a number smaller than negative 3/2, it's a negative cubed is a negative, and greater than 3/2, negative 3/2 here is a positive, cubed is a positive. Well, 1 is over here. So everything for all x greater than or equal to 1, f of x is greater than 0. So check there. Then I need to prove that it's continuous. So it's continuous on negative infinity to negative 3/2, union negative 3/2 to infinity. So it's continuous on 1 to infinity. Check. And then I need my derivative here. So f prime of x is going to be a negative 3, 2x plus 3 to the negative 4th times 2 is a negative 6 over 2x plus 3 to the 4th. So I know this is always going to be positive down here. This is a negative over a positive is a negative. It's always decreasing on both pieces here. I know it's undefined. There's a vertical asymptote at negative 3/2 here, but To the left here, this is going to be negative and decreasing. To the right here, this is going to be negative and decreasing. I'm interested on the interval from 1 to infinity here. So it's going to be decreasing on negative infinity to negative 3/2, union negative 3/2 to infinity. So it's decreasing on 1 to infinity. That means that the interval test applies. One to infinity of 2x plus 3 to the negative third dx. It's going to be u is equal to 2x plus 3. Du is a 2 dx. 2 and a 1/2. This becomes 1/2. U is going to be 5 there to infinity of u to the negative third du is 1/2 limit as b goes to infinity of 5 to b u to the negative third du is 1/2 of u to the negative second over 2 evaluated from 5 to b. This is limit b goes to infinity. It's 1/2 of 1 over 2b squared minus 1 over 2 times 5 squared. That 1 over 2 can come out as a 1/4 of b goes to infinity, 1 over b squared minus 1 over 25 is 1/4 of 0 minus 1 over 25. See here, this should be a -2. This is a negative and a positive. It's a negative and a positive there. That's 1/4, 1 over 25. So 1 over 100. So converges by the interval test. All right, this next one is definitely a little crazy. So just want you to think through this one. Number 24, it's an even number problem, and it is, just put on your thinking caps here. So we're going to do it for the simplest case, but we're going to prove, maybe not prove, but we're going to state how it can always be solved. It's just going to take more steps of integration by parts, but we're going to find the lowest case here. So the lowest case here is when n is equal to 1, and k needs to be a positive integer, so k needs to be greater than or equal to 1 here is what this is saying. So let's just look at x to the k here, where we're going to look at, for example, x to the first, x to the second, x to the third. We're going to look at that. So x to the first, x to the second, x to the third, dot, 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 dot. I'm just going to look at these various graphs here. just at the positive part because x needs to be positive here and k needs to be positive. So then I get y equals x, y equals x squared, y equals x cubed. It's going to grow a little faster than that. Y equals x to the fourth. Going to grow faster than that. So on and so forth, like that, right? And then let's look at this other part of y equals e to the negative x is like this. Backwards 0, 1, like that. So these are always positive numbers, and these are always positive numbers here. So the product of two positive numbers is always positive. And then for continuity, because x to the k and e to the negative x are continuous everywhere, their product is continuous everywhere. All right. So right now we're looking good for the entire n equals 1 to infinity. So this one's going to throw a monkey wrench into it though. So f of x is equal to x to the k, e to the negative x. And we're going to use the product rule here with u equals x to the k. V is equal to e to the negative x. U prime is equal to k, x to the k minus 1. V prime is negative e to the negative x. So we have f prime of x is equal to u prime v plus v prime u. Now we're going to factor that and say that there is a x to the k minus 1 e to the negative x that comes out and leaves me with k minus x left over. That's equal to k minus x, x to the k minus 1 over e to the x. So all of these values here are still going to be positive. They're just all these graphs over here got shifted 1 to the right, but they're all still positive numbers. This is still a positive number. It's this thing that's in question, but let's go ahead and look at the x values here. If we looked at the other side of the graphs over here, sometimes we could run into a problem with it becoming negative on these odd powers on the other side of x equals 0. So I'll put 0 for a critical number here. And I'll also put x equals k as a critical number here. No critical numbers for the denominator there. And so when let's say when k minus 1 is, let's not worry about that. So I'm interested in this piece over here furthest to the right is what I'm trying to figure out. So x is going to be a positive number. This is going to be sufficiently large enough here where this is going to become a negative number because it's going to be greater than k. So this is going to be a negative times a positive over positive is going to be a negative, and it's going to be decreasing for all x greater than or equal to k. I really don't even need to worry about these because I need some value that I know that it's always decreasing greater than or equal to that. So what that means to me is that I need to peel off the first k minus 1 terms of my series, and I'm going to just show you the easiest form of this is going to be let k equal 2. Okay, k equals 1 is too basic. So I'm going to look here and say, all right, if k is 2, then I'm dealing with a derivative of 2 minus x. X to the 2 minus 1 is 1 over e to the x. This is my f prime of x when k is 2. All right, so that would be decreasing on the interval k to infinity there, in this case from 2 to infinity. So let's go in there and let's put k is 2. So n squared e to the negative n equals 1 to infinity. So if k is 2, I'm going to have to peel off the first term. K minus 1 is 1. So I'm going to have to peel off 1 squared e to the negative first plus n equals 2 to infinity n squared e to the negative n, like that. And now it should be positive, continuous, and decreasing for this part right here that I can use the integral test. So this is going to be 1 over e plus integral from 2 to infinity of x squared e to the negative x dx. I can do this because I've proven that when I peel off that k minus 1th term there, that this is going to be positive, continuous, and decreasing for what's left. So I'm going to use integration by parts with u equal to x squared, dv equal to e to the negative x dx. Du is going to be 2x dx. V is going to be a negative e to the negative x. It's going to be 1 over e plus, and this part really doesn't matter. It's not going to change convergence, those finite number of terms there. But I'm just going to write it out anyways. Plus, let's see, uv squared b goes to infinity of x squared e to the negative x from 2 to b plus limit or minus limit as b goes to infinity 2 to b of v times du is going to be 1 over e plus, and then exponential is going to grow faster here. It's going to be a negative x, negative b squared over e to the b. That grows faster, it'll go to 0, plus 2 squared is 4 over e squared plus 2 limit as b goes to infinity of 2 to b of x e to the negative x dx. 1 over e, this is plus 4 over e squared plus 2, and then u is equal to x. dv is e to the negative x dx. du is dx. v is equal to negative e to the negative x. So this is going to be 2 times uv to b minus 2 limit b goes to infinity 2 to b of v du, like that. It's going to be 1 over e plus 4 over e squared. And then this is going to be, again, when e to the b is in the denominator, it's going to infinity. That's going to go to 0. That's going to be a negative 0 plus 2 over e squared. And this is going to turn into minus 2 limit as b goes to infinity. E to the negative x, 2 to b, like that. So this is going to be 1 over e plus 8 plus should be a 4 over e squared. That's a 2 times that 2 is 4 plus another 4 over e squared. And then this is minus 0 minus 2 1 over e squared is going to be 1 over e, and then 4 plus 4 plus 2 is 10 over e squared. So it converges by the integral test. And all that's going to happen if k increases is I'm going to have to peel off more terms, and this x to the k gets bigger, and I'm going to have to do more integration by parts, but it's going to come out and it's going to converge every time that I can do k plus 1 iterations of integration by parts here. So I had to do integration by parts k times, and then I had one more integral to do after that. So I had to integrate 3 times total when k was 2, but integration by parts twice. That's why I picked a small number like k equals 2. So I possibly had room to do that here. So let's go ahead and move on here to this next example, which is like number 30 from 9.3, and we're going to need to recall theorem 8.7. This is referenced in the text to tell us that it converges in this case and diverges in this case in 9.3, but you have to go all the way back to 8.7 to see what it converges to. But that is p, that's a p minus 1 in the denominator down there. So we'll be able to use that theorem here. Let's just prove that this is positive, continuous, and decreasing. So 1, we have if f of x is equal to 1 over the square root of x is basically what we have. Then function does not exist over here for values that are less than 0 for over here. It's going to be positive, so check that it's going to be positive on 1 to infinity. 2, it is continuous on the interval from 0 to infinity. So it is continuous. Let's make this open. On 1 to infinity. Its only discontinuity was at x equals 0 because there's nothing to the left of that. So it's continuous on its entire domain there, maybe excluding that vertex depending on how you define continuity there, where it only comes from one side. And 3, so this is f of x is equal to x to the -1/2. So f prime of x will be a -1/2 x to the -3/2 is equal to a -1 over 2x to the 3/2. And so let's look at our sign chart there. We have our vertical asymptote at x equals 0. Actually, we just have the critical number here. X equals 0. Not defined in our original there because we can't have 0 in the denominator. So the function does not exist over here. Over here, this is always going to be negative and decreasing, so it's decreasing on 0 to infinity. So it is decreasing on 1 to infinity. So I don't need to peel any terms off. So integral from 1 to infinity of 1 over n to the x to the 1/2 dx is equal to let's say by theorem 8.7, since 1/2 is less than or equal to 1, this diverges and this sets us up to be able to use the p-series test now that we have this theorem, and know that we could use the integral test to prove this, but we don't want to every time. So based off of these p-values, we should have a new theorem called the p-test, p-series test, and we're going to go ahead and use that for our last example here, like number 35 in the textbook. So this appears to be the summation from n equals 1 to infinity of 1 over n to the 3/2 power. I see the n and then another n to the 1/2 here. 1.5 is 3/2. So since p is equal to 3/2, which is greater than 1, the p-series converges by the p-series test. If we actually want to know what the integral converges to, we can find that, but that has nothing to do with what the series converges to. Just if the integral converges, which it will, if p is greater than or is greater than 1, then the series will also converge. So that's it. That one was pretty easy to use the p-series test. We like the p-series test a whole lot because it's easy to use and we don't have to show all the requirements for positive continuous and decreasing to use the integral test because we've already established that generically for 1 over x to the p that it will converge in the instances where p is greater than 1. So we just use that fact now as a new theorem, theorem 9.11, to tell us that anytime we have a p-series, we can just go ahead and look at the power p to determine convergence or divergence of that p-series. All right, that's it for this video, and we'll come back next time and talk about some supplemental examples from 9.4. See you for the next video.